Okay, let's start. I will not show how to move or how to wherever here in Houdini because it's fairly simple and there's a lot of tutorials about that. This is a relatively advanced tutorial, so I will get through that. But let's start with the beginning and just create a sphere here, and I will create a sphere in Maya as well. And let's see the differences between them. So when you create a sphere in Maya, you can see there's some inputs already. So if you just hit here the shapes, you can see we have now a transform and a shape. So every object in Maya, every geometry object has at least two nodes, which are transform and shape. You can see those nodes here in the node editor, and you can see that we have a little bit more. Just forget about this one. This is the shading group for shading. But we have the transform node and we have our shape. Our shape is what defines our object, where the vertex are and how many are there and all this kind of stuff. And here we have a node, which is the sphere, where we can change things about the sphere, like how many subdivisions we have in the sphere. And it goes to the in mesh here in the shape. Okay, and that's a transform. The transform is what moves the object. It's a group that it's above it, and the shape is just a child of that group. It's really, really important to understand that this is just a group. Sometimes people don't get the difference between the transforms and shapes that well. So we can just do Ctrl-G to do another group and put it like there. And we can parent this shape to the group, just hitting here, parent. I can spell it correctly, parent. S and R, and now the shape is moved where my parent is, which is a group, and we can do the same thing again, and now here it is. So when I'm moving the object in Maya like that, I'm just moving its parent. I'm moving the group above it. If I want to move the shape in Maya, I can do something like that, and now I'm moving the shape because I'm moving the vertices. I'm not moving the group. As you can see, the group is still here, and now I can rotate from here because I have moved the shape. The same thing happens in Houdini, where this group here is a transform, and you can go inside, double clicking it, and you are in the shape node. So we don't have really a shape node in Houdini. You can say that all of this space where I can load lots of nodes, these are the shapes. This is the shape. This is really where my object is defined. Right now, we are in the geometry context, which is the one that defines geometry. And I'm sure that you have heard a lot of subs and robs and dobs and all these strange names. Well, this is a sub, this is a surface operator, and rob is render operator, and dob is dynamic operator. They call it that way, but just think of it about this is my shape. This is where I do things. As you can see, I already have the same sphere that I have in Maya. I can put the same parameters here. It's exactly the same. So let me just undo this to get the same thing. And as you can see, we don't have this one. This one is all the context, but we have this one. But if I just hit here and create a smooth, you can see that we have now another node right there. We have my polysphere, we have my smooth, and the shape. So I can do exactly the same thing in Houdini, creating a subdivide node. And now I'm subdividing. I have exactly the same geometry in both softwares and more or less the same node tree in both softwares. So in Maya, you're used to get rid of all of that. Once you're happy with that, I know that a lot of you are just using Alt-Shift-D, or you can come right here and delete history, and you're doing that a lot of times. Because if you have a really complex tree here in Maya, Maya crashes, and Maya doesn't really want that. You want to get as few nodes as possible, and that's not what happened in Houdini. In Houdini, and that's why it's called procedural. You don't have to delete anything. You can have here lots and lots of nodes, and you can always change this one, the input, and you will have another output. So this is why this software is really, really good to do a lot of stuff. And we will try to understand how to use it to make a Ziva-like muscle system just inside Houdini. And that's it. That's it for now. Let's see you in the next one. Okay, let's start with the first basic muscle setup. Let's just bring up a geometry node, and inside of here we will bring an alembic node, and I will load up our friend Mr. Ink. We have this animation. As you can see, it's going really, really fast. You can hit, by the way, D here in the viewport, and you can change a lot of stuff in the viewport, and you can draw your time. And as you can see, it's going higher than 120 frames per second. You can hit here the clock, and it will just do 24 frames per second, or wherever your project is set up. And the thing is that it's really, really fast because it's a packed alembic. Houdini, by default, loads the alembic as a packed alembic. That means that this is not really geometry. This is another thing. This is just a packed thing that you cannot work with, but you can see. So it's really useful in a lot of cases just to see it, just to have a reference, just for lighting or whatever. But for us, it's not really useful because we need the geometry to attach things to. But let's see this guy first. And you can see we have a lot of stuff here. This guy is bypass, which is really don't do anything with this node right now. As you can see, the blue one is to show things, and whatever if I do here just a sphere, just to wherever my blue click is on, I'm just showing my sphere right there, and I can show my alembic right here. We have also the template. So I don't know if you can see that, but there's our sphere template. And that's pretty much it. But the thing, as you can see, is this guy is huge. You know, the sphere was really, really, really small. That's because Houdini works with meters and Maya with centimeters. So this guy right now, if I hit 1, 2, sorry, I can do that here, 2, 3, this is a front view, and 4, which is a side, view. These are 25 meters. So this guy is huge. First thing is to create a transform, and just 100 times less than that. Nothing happens because I don't have the blue tick there. Let's do it. And now this guy is about a meter and a half. By the way, I'm using F to frame everything, just like in Maya. So this guy is a meter and a half. Okay, that's better, much better. But it's still no geometry. So we need to unpack it and see this unpacked, and you have some lines here, which means we have geometry. With Shift W, you can change this, and also with just W, you can do the wireframe or not wireframe. Okay, so now we have this unpacked, but I usually do, just to keep safe, a convert node to be sure that there's unpacked polygons. You can see right now, if I hit play, we are around 50 or 60 frames per second, because now it is really calculating every vertex and everything. And another way to see that is that, as you can see here, I can hit my I button to get the info. This is my information tab. And right now, this guy has 29 points, 29 primitives, 29 vertices, and 29 packed alembics, because there are 29 objects here. But it doesn't know how many vertices are there in any of that object. As soon as I hit unpack, you can see in the info that we have 20,000 points, 29 primitives, 80,000 vertices, and polysubs. Just don't worry about that right now. And we have also attributes here, and we have one attribute, which is the P, which is the most basic attribute there is, and this is the position in 3D space, so X, Y, and Z position of each vertex of each frame. So if you can see here, I have one attribute that is called path that I have lost just right there. This attribute called path is the path to the alembic object. So if I hit S to select, and I say, let's select alembic paths, you will see, somehow you should see right there, the paths to the alembic. This is just like your liner in Maya, and it can save all the hierarchy that you have in Maya and groups and whatever. But right now they are just the shapes, as you can see. And this is just an attribute, which is a string, just letters and characters that defines where my objects are. So this is really useful to do a lot of stuff. But as you can see, we have lost that here. It's really easy to fix. Transfer attributes, we will do a path transfer attribute. So now my unpacked Alembic, my geometry has this attribute called path. Great. So let's grab that one and just make a duplicate of that. Alt, by the way, to just select Alt and drag and you duplicate in all the nodes once. And let's grab my Alembic and load the muscles. Okay, now I have my muscles right there. And I can try and just select one muscle because we will be doing like the first setup in, say, the biceps. So I can do a blast node, which deletes everything right now. And I can choose what thing to delete. And thanks to the Alembic path, I can select this guy, hit enter, and I just deleted the biceps. I can delete non-selected, and now I have my biceps. And as you can see here, this add path, it means attribute path equals all this string, all these characters. Okay, so now we have our muscle. There's a better way to do that, but this is fairly good because sometimes you can do something like that. Just as an example, instead of choosing paths, I will select geometries and then maybe grab this guy, which is called Island 6108. And this will change. As you can see, this doesn't define anything. This can change a lot. So that's not a really good way to do it. Even worse, to get the points, maybe I can double click. I can select some points. I can double click, hit enter. These are the points, but these will change a lot. And if I just do the same thing with another topology or whatever, it doesn't work. So it's fairly better to just rely on the strings, on the name of a thing, and that's it. So just to end everything, we will create a null and we will name that out bones, and we will do the same thing here. A null is a node that doesn't do anything, but it's better to have everything organized so we can know where we are and how we work. I just wrote that in capital letters because it's easy to find later what you're doing if you have everything in capital letters. Well, not everything, but the outs, as an example, the things that you want to get really quickly. Okay, so that's it. Let's start building our first muscle setup. Okay, so let's start with the first setup that we can do. So I can create an object merge right here to be organized, and I can just call this guy to get this node. So right now, these two are the same, but you know, it's better to get things organized. And the thing is that I wrote in capital letters these two guys just because when you select them, just let's say I want the bones here, I can hit here and look for anything that I want, and the capital letters one will be the first ones, so it's easier to get them. So now I have my bones, I have my muscle. Great. My muscle is moving, and I don't want it moving, so I can create a timeshift node. I can spell it. Timeshift node, yeah. And this node is already with an expression, which is $frame, which is the frame that we are. Just saying, okay, just show the frame in the frame that we are. So I can delete this channel and just keep the frame one. And now I have my muscle without moving and my bones moving as they should. Great. First of all, we will do a group. You can do groups of whatever you want and in a lot of ways. We will be doing a group just by selecting the stuff. It's not the best way to do it, but I will show you on another lesson how to change that. So let's grab some points right there. You can change right here if you want like a square, like a lasso, wherever. Shift selection and adds the selection. Control removes the selection. Really normal stuff right there. And just hit enter and you have here all the point numbers that you have selected. As I said, this is not really great, but just for the sake of time right now, we will do our group like that, and we will name our group like attach point. Great. Let's convert that to a hydral soft body. Hydral soft body. Vellum hydral soft body. So what this does is it just creates like a fem object, just like in Ziva, and that means that we have some points inside this guy. I can create a clip node to show you that. So let's hit the clip and add a little bit of that. Yeah. So as you can see, this guy has nothing inside, and this guy now is triangulated, and it also has some points inside. We can just reduce this scale, and we'll have more points inside. Well, it's not really that useful to have a lot of points inside and not that many points outside. So let's keep it that way for now. And you have this thread conform, and you also have the soft body itself. Here you have all the attributes that you had really in Ziva, in the Ziva object, the mass and density and all this stuff. And the most important one is the stiffness, which is similar to the Young's modulus in Ziva. So you have a number, you have your times 10 thing just right there. Let's keep it simple. I will not do anything else. And let's create a vellum solver. We need the solver to do all the calculations. And we will add just a ground plane to our first simulation. This is our first simulation. As you can see, this is a soft body. And if I change the Young's modulus, the stiffness just right here, as you can see, this is much softer, or something that this is really, really hard. And we have like a really nice simulation. Set Shift W. We have this kind of simulation, which is really, really nice, where you can see that the lower the number of points, the less stiff it is. But we will keep it as it was and just hit play. And this is fairly nice for a muscle. Okay, so we have to attach that to our bones, which we have our bones here. So let's create an attach node. Attach, it's anything today, attach to geometry. I just put it right there. And just for you to know, there's always 3 inputs and outputs in vellum, which are, the first one is the geometry, the second one is the constraints, and the third one is the collision object. So I can show you that a little bit better. So this guy is my geometry, really. This guy is my constraints. It's almost the same, but it's really not the same because these are the particles that are calculated from vellum. If I just try to do something here, let's do the attachment. So I will attach to the bones. And right now you can see every vertex, every point of the muscle is trying to find the nearest point in the surface of the skeleton. So that's the way we can create an attachment. And as we have done a group, we have a group here in the attach constraints where we can define our point group, which is called the attach point. So now only the group that we did is attached to the bones. And we can just simulate that, and you will see that now the attachment is working. It's not really that stiff. And also there's no collisions really happening at all. That's because in our solver, we have no collisions. We can just do something like that. Or as if we already have these bones connected here, we can just do that and keep it cleaner. And also, as you can see right now, this constraint thingy, it's looking a little bit different because we have this attached constraint done. So really, it's covering the particles that it puts in those vertex and giving them some width. And we can just try and hit play right now. And now we have collisions and we have a hanging biceps. doing lots of stuff. We can try and change that, put much more stiffness and see if that works, but that won't work. And I will tell you why. And that's really the most important thing to think about. Stiffness is calculated in a way that needs a little bit more sub-steps in the solver when you want really high stiffness. So if you want really low stiffness, things that are hanging a lot, you can make do with just one sub-steps. But as you change that guy, you will see obviously everything is lower, but now the stiffness is calculated a lot better because it has more steps to calculate it. And that's not really good because we want the fastest simulation possible. I'm always rooting for doing everything as fast as I can so I can have more iterations. And the best thing that you can have is a lot of iterations, and then just choose up which one works best for you and maybe mix and match all the iterations that you have. So at the end of the day, you can do something like that and try to get something better. How can we do this? How can we get something better with that speed? Well, we can do another attachment, just an example, and put it right there. Now I have attachment to all my points, and this attachment also have a stiffness, and I will reduce it a little bit. So now everything will follow. And second attachment that I have is much loosened. It's not that hard. So you can have some movement there, and it makes it work nice. We have a nice jiggle in our muscle. We have everything working, and it's really, really, really fast. You can see right there, if I just delete my simulation, and instead of hitting play, I just go to the last frame, and you will see right here how it's doing the calculation. And you can see as I speak, we're already in the 82 frame, in the frame 82, so it's really, really fast. And we have done like 240 frames in like 10 seconds, something, 15 seconds, 16 seconds. Yeah. So that's the speed that we have. It's really, really fast. It's much, much faster than Ziva. And we are also calculating all the collisions right there. So we have our first muscle. That's great. I will stop it here, and then I will do a couple of things to that to get even better simulation and better speed. See you in the next one. Okay, so now that we have our simulation working, let's talk a little bit about those guys. Stiffness we already know is Young's modulus. Damping ratio is trying to stop the inertia and velocity of the jiggling, really. So if I put like a lower value, you will see that this is much jiggling right there. And if I put a higher value, something like that, oh, the other way around, sorry, this will be much more jiggly. And the lower the number, the less jiggly you will have. Okay, and reference scale is really the length of each edge at the beginning of the simulation that the simulation will try to go to. So if I put a lower value, you will see that our muscle shrinks at the beginning, just at the first frame, because it's trying to get half the length of the initial geometry on its edge. If I put something bigger, you will see that it will expand because it's trying to maintain 1.5 times the edge length of each edge in the simulation. So this is really what's happening when you do the excitation and line of action thing in Ziva. They are changing these values to emulate when the muscle is full of blood. So when it's full of blood, the length scale will be maybe a little bigger because it's much bigger because it's full of blood. And also the stiffness is much higher, and maybe the damping ratio is a little bit higher also because the jiggle should be much, much faster. So how to do that? Because right now these values cannot be animated. If you put some animation here and you change the value, the solver won't work and won't pay any attention to that. because this is just initial values. If you want to do some animation and change these values during the simulation, you have to go inside the solver. And one thing important to know is that change entering here, you can just do that with the Houdini FX license. The Houdini Core cannot do that. But there's a workaround on that. You can just do the setup in an FX license and then do all your shot work in a core license. And that's the only thing that we will use from FX, really, Houdini FX license. So everything else can be done just with the core license. So let's create here inside the solver constraint properties, and let's do some really animation, really simple animation. Maybe the rest length, which is the easiest to see. So maybe we can go there and do here some animation and just put it right here and put it half scan. Just alt click and I'm doing keyframes right there. So now you will see that it will shrink, as you can see, during the simulation. Great. That's a little bit what happens when we use line of actions, but for sure we need to do some line of actions there. So let's try and make some line of actions. Let's create a blast node. Really easy, really fast. And I will select just a couple of points, maybe this guy and this guy. Invert the selection, so I have 2 points. I don't know if you can see, there are 2 points right there. We can use an add node to create a line between those points, just like that, just selecting by group. And it tries to get the points that we have and do a line with them. So right now I have a line, and as you can see, is already following my skeleton. You can see right there, this is the skeleton. This is my line, and you can see we have already a line of action. Great. So what we need to do is to measure this line of action. We can just do a measure node and use the length of that. It will create an attribute called perimeter that we can just see right here. For seeing these attributes, this is the key to hide or show the attributes. And also you can just right click and hit here on the pencil and change how you want to see them. Maybe you will use a color, maybe you can use the marker, which is the text. Sometimes it doesn't work, but you just click and click and that's it. And you can also change maybe the font size to get a really huge number right there. And maybe another color to be able to read it easier. So right now, this is my length, and as you can see, it changes as it moves. Great. So this is exactly how the line of action in Ziva works. It's just measuring the line of action and just giving some information to the muscle to do some stuff. So we can just grab this attribute right here and do a remap. You have done some rigging or some look dev in Maya, you know, the remapping attributes is a thing that we do a lot. So maybe we can just start by computing the range of the attribute. I have to say which attribute I want, which is a primitive attribute right now, and that's a perimeter, and that's the range that we have right now. So let's say that this is the input max, and the input mean, let's say it's a little bit lower, and we will remap it to maybe 1 and 0.8. The other way around, 0.8 and 1. So now when it shrinks, I have this number, which will be my resonance scale, and we will be doing the muscle a little bit smaller in this case than it is when it's not excited, when the forearm is not bent, so the bicep is not working. So let's do a little bit higher number here, something like that, even something like that. So it's 1 and then it goes to 0. I think it's too much, but that way we will see what happens. And we can create a new attribute that we will call rest or length, just to be easy with that. Okay, We can do another one. And this time I want to create the stiff attribute, and that will be like 1 and 100, maybe. Let's show this stiff attribute. As you can see right now, our stiff attribute is showing as a color, so we will come here and make it show as a marker, and again, large, maybe just like that. This is going the other way around, so it's like that. And the stiffness will go up 23 times because we will be multiplying it what it is in the default. Let's do something like that so it's really noticeable. So it will be really, really stiff when the muscle is excited, is contracted, is full of blood. Great. There's a thing that we have to do right now because, as you can see, we have this is a primitive attribute, so it's going with the primitives, not the points. But the best thing to do right now is to convert that to a detailed attribute. The difference is the points attribute saves data. It can be a string, it can be a float, it can be a vector, it can be whatever it is. In every point, same thing with primitives, in every primitive, and detail just save it one time. So it's just one for all the object. And that's what we want because it's much, much easier to control and to save, because we don't have to save that much numbers, really, that much data. So we have this attribute promote here, and we will change the primitive attributes called rest length and stiff, and we will change it to a detail attribute. So now they are detail attributes. So the detail attribute is just one float. As you can see here, FLT for float, one number for all the object. Same thing with the stiff. Not for all the primitives, not for all the points, just one number. In this case, it's just a line, so it's just 2 points, but you know, it's a double. It's really the double the data that we use. Okay, let's create here a null, and let's call it out line action for the biceps. Great. I will hit Control C just to go here and do a Control P. So this rest length scale shouldn't be an animation anymore, but we will do an expression getting the detail attribute that we did. So it's detail, open parentheses, and you can see Houdini is really smart in that, and he tells you how to use every one of the expressions with this. So the surface node is our node, the attribute name, and the index is the index of the attribute value that we want. In this case is 0 because we just have one float. So we can do exactly that. I hit Control Z on the node, so I can do Control P right there, and I can just put rest length, which is the name of our attribute, at 0, and that's pretty much it. So we can see that now. Let's just, you can see it's working. I just disabled the simulation right there. You can see it's working, and now it's changing our rest length scale using that attribute that we did on the timeline. So that's great. And let's copy that and paste it just right here and change rest length for if. We have it just right here, and you can see that the stiffness goes from 1 to 100. One thing that you have to keep in mind is that you're overriding the stiffness that you had. So usually your stiffness is 1 times 1000. So we will have to change that. So now it's times 1000, and when we get the muscle excitation, it will be 100 times more, 200 times more. So let's try and do that and do our simulation right there. Oh, have the simulation on. Let's put it on, and you will see that it will change a little bit. It's very noticeable because there's really no changes at all. but we can try and do a lot more frames. I don't remember how long this simulation is, but it's fairly long. So doing that, we can create a line of action, as you can see right here, and connect this line of action to our muscle. So we will have the excitation right there. And that's a really, really nice thing to do. There's a lot of things to talk about that. And I will talk about that in another video, where I will show you the way I do it. This is just like a starting point to get used to the nodes and the workflow. But it's not at all how that should be done, really. Maybe we'll see some variation right there. I don't know. You can see some excitation there, not that much. But yeah, it's moving, it's working, everything's fine. And we can even do something crazy like let's get this measure attribute, and I will do another remap just for the sake of visualization. So let's get this guy, and this guy will be like that, I guess. So let's see this one. It will be excitation, just to get something visually there. And let's show as a marker. So now it's 0, now it's 1. Great. We'll have to change this guy. So now we have some excitation right there, not that much, something like that. Okay. So now what I can do is just grab this guy, Control C again, and we can do color. And we can do, well, I think we can, yeah, we can not go promote here. And again, promote this to a detail attribute. And I will do copy attribute. I will explain this node because it's really, really powerful. So I will copy this attribute to this object right here, and the attribute to copy will be excitation. Great. So now we have to tell them that it's, I cannot do it like, okay, let's do primitive and primitive attribute. Okay. So now I have excitation right there. And I can show it as a color. So now you can see it's getting whiter when it's excited. So it's really, really nice. We can do something like apply a color to it and make a run from an attribute, use excitation. And I think that they cannot be, and remember that. Let's hide this guy. Yeah, that's the thing. So now we can see the excitation in a really, really great way. So you can see when the muscle is excited and when not. Great. Just to show that we can do a lot of stuff here, just to do some visualizations of things. Right now, this line of action is not the best it can be. You can do a lot of stuff with that, and you can do it much, much better than that. But it's just an example to show how you can do all of these things here. So that's it for this video. We will do another one. I guess that we will go to the fascia and skin and all that stuff. And then we will try to show a nice workflow to use all of that in a full body muscle simulation. Great. See you in the next one. Okay, so let's go to the fascia. You come from Ziva. I guess that you already know what a fascia is. If not, you will see it just in a moment. Let's duplicate this guy, and I will bring up the skin of Mr. Ring, but just one-sided skin. This is one-sided geometry, nothing really fancy there. Then I will bypass these guys, so we have all the muscles moving, also the bones moving. Everything's great. So I can select both of them, and with Alt move it so I have a merge node. And here I will do a null, which will be moving height, that, and then a time shift, which is just reading, remember the frame where we are. We just delete this channel, and now this is not moving anymore. So I can do another null and call it static collider, something. Okay, so now that I have here my skin, I will do a fascia from that. It's really, really, really easy, simple. We will do a vellum cloth. We will do a vellum pressure. Well, let's do just the solver right now, and you will see how it works. Let's grab this guy. We can do Ctrl-C also and do an object merge and bring up those colliders without moving. These guys are moving, great. Put it in a collision and just get the rest length scale to something like 0.5, and we will see what happens. We can just do like 10 frames of that to create our fascia. Okay, this is working, as you can see, but we have a couple of issues. This issue is interpolating and these guys are moving, so let's try and fix that. Really easy to do. We can do a group to get these guys right from not moving, just like when we did in Ziva, but we can do that a little bit better than we did with the muscle, so a little bit more procedural. One thing we can do is do it from insert edges and create boundary groups, and you can see that it has created a lot of groups. So this group is every point that has another point that has shared edges, and all those groups are the other ones. So now that we have all those groups, we can create another group node and choose those one. So if I choose this one, you can see it's everything. But if I choose this one, it's just this guy. And then I can choose this one, and so on and so forth. And we have all of them. That's nicer. And just imagine this guy will have like a tail or something. It will be having another hole right there. So each hole will be on our, let's call it, borders tool. And we can do a little bit more, because if we have another, it will be called group 1__4. So we can just delete all of that and put here an asterisk. So everything that is called group__, whatever number it is, it will be on that group. So our borders group is procedural. We can change this geometry, we can change this input, and this will always select the unshared points. Great. So now that we have that, we can just go to our vellum and say that the vellum cloth, where is, yeah, pin points. We can pin the borders. We don't have to match animation because there's no animation here, but these points will not move. So now I can do the same thing that we did, and you can see it's much better. You don't need to do a ramp like in Ziva. You don't need to do almost anything. It's working really nice. We have a problem here, which is this guy penetrating, and that's because at the beginning, the first frame, you can see some blue right there. So really, really easy to fix. There's another, it's called peak, which is really nice. And what it does, it moves the points on their normals. So you can see, you can do crazy stuff here. But the only thing that we need to do is put a really low number there when just to get a little bit outside of the collision geometry, and that's pretty much it. Great, but we don't have that much resolution right now for a fascia, so we will do a remesh. Maybe better to do it as everything is procedural. I don't care about where I put it, but I think it's better to put it just right here, and we will do a remesh node. And the remesh node can do a remesh with triangles, which will work really, really well. So we went from 8,000 points to, let's say, 17. This is not that much. Maybe we can do a little bit more. Let's try to do something like that. This is much better, even more, much better. You can see we have these strange things because this guy has these quads. I really don't care about that because we're deforming it in the simulation, but if you want, you can always put some subdivide nodes just in between, and that gets rid of that because we're just remeshing the subdivide one. But we don't really need that because we will be seeing wherever it happens in the simulation. Obviously, the simulation will be much slower because we have lots of points, but it's pretty fast. Okay, so what we did right now is not only the length scale to make it shrink, but also some inner pressure. So we can create a pressure node, vellum pressure node. Oh, it's been a while for me. Sorry, guys. Let's do a balloon. There's a configure balloon, and it comes with a pressure node, so I can just grab it and put it there. Great. So now that we have that, we can see that the pressure is going the other way around. No worries about that. We can get the pressure and do the same thing with the length scale, something like that. And now we will see that we're starting to have something like a fascia that looks really, really, really nice. Okay, there are some issues here and there, obviously. I think that's too much, but yeah, I think we have a lot of geometry in there. But we can maybe that's a little bit. Oh, I don't care. Let's just give it that way. Yeah. So it's not perfect at all, and you can also see that we have too much resolution, and we start to see the geometry underneath and the quads underneath. So I think that's too much resolution. Let's do it something like that. And let's try to solve this one. So that's one a little bit better, but as you can see, you can go as up as you want in the resolution, and it's still fairly fast. There are some issues here and there, but you can, as you know, you can just grab that guy and go to Ziva or whatever and just try to get that fine detail. I'm just trying to show you techniques to do muscle and stuff, so don't worry that much. So let's save this guy as our fascia. Let's use a file cache for that. File cache comes with another thing already done for you, like the name and this construct name, which is going to be in my folder and files and geo. It will create this folder and all of that. But if you want to see exactly what you're writing, just hit explicit and you will see here the expression, which is $heap, which is the folder where my heap file fascia construct is. It will do a geo folder, then my heap name, which will be fascia construct $OS. $OS means this guy right here. $frame is the frame, and bgeo is the format Houdini saves the caches. SC is the bgeo compressed. So if I middle click here, I can see what the expression will do. But as I said, the folder, files, geo, fascia construct, which is my scene, file cache 1, which is this guy. If I change this guy and say fascia v1, this will change the fascia v1, and the frame and bgeo and the scene. So I don't want time-dependent cache. I don't need the dollar frame because we will do just one frame, the frame that we are at. And maybe we can just save it like that. So let's just hit save to disk. And now I can disconnect this guy, and this guy is already my fascia. Great. We have constructed our fascia in 10 minutes. That's not bad at all. And let's see what happens here, because I have a lot of things right there. I have a lot of vellum attributes, the groups and detail attributes. I have a lot of stuff. So I don't want all of that. I just want a geometry. So what we can do is not load it from disk, but create an attribute delete and delete everything. All deleted. I don't have any attributes. I have a lot of groups. I can do a group delete. Same thing, and I can do that. So I'm deleting all the groups. So this is really, really clean. But I want to keep the border groups because no, we already have it. So we can say, okay, delete everything, but using this symbol right there, border groups. So right now I still have my border group and nothing else. So the file cache will be much smaller in size. So that's really, really great. And I can just do something like that, or maybe just keep that as a construct, and then I can just get this guy, Control C of this guy, and just do a file read node and read this guy. So I have this guy with the borders and everything and nothing else. Great. Okay, so we can do the same thing, and in fact we will be just doing exactly the same thing. So we get these three nodes, put it right there, put that, and maybe we can, sometimes I do a couple of passes of the same. You will see what I mean, because now that we have a fascia that's already in place, we can do exactly the same thing, and it will try to get to a better position. Right now, that's not happening. It's going really, really crazy. But what we can do maybe is just put a little bit more sub-steps to get better collisions. This is going to be much slower. But maybe it will give us something better. Not that much. Okay, as you can see, with more, maybe we can do that on the first one. Let's just hit escape and let's redo this guy. Escape. Let's redo this guy with 4 steps. Let's see what happens. Because sometimes you can just creating the fascia. It's much easier to, and you get a better result with a little bit more sub-steps. I'm not sure if that's the case. Now, let's just wait for it. Okay. Let's compare these two. Yeah, I think it's much cleaner. Yeah, let's keep it that way. Yeah, that's great. So let's save this guy. And now this guy will load. And that's much cleaner. Okay, so now we can try, and instead of getting the static collider, we will get the moving collider. And we will get that just right there. And what we will do is get read for now on the vellum pressure, and we will use an attached to geometry, because if we don't have the attached to geometry, all the borders will not follow as it should. So let's attach to our muscles and bones, but just the border group. So right now, this will be attached, and we can try some frames right there. And there's something really wrong right there. I really don't understand why, but not worry. So we have this guy. We have that guy. Oh, I guess that's wrong. Okay. It's not working that well, right? Yeah. Why is that? I don't understand why it's not doing what I want it to do. Okay, no worries. I have my border. Yeah, that's sure. Yeah. Okay. Because I was pinning to animation. I guess that's the reason why it's behaving like that. But now it's okay. Now this is working. Great. So as you can see, we already have something nice. Obviously, we will need to fix a lot of things here, but this is working pretty nice. And amazingly fast. Really fast. So we will try to do one thing here. Is I don't like that happening at the beginning, so maybe we will try a couple of sub steps there. See what happens at the beginning. Yeah, that's not working at all, and I think it's not because of the substep, but because of the vellum cloth that shouldn't have the resident scale, because we have a nice. Yeah, that's the thing. He was trying to do something that it's too much for resident scale because it's trying to make the edges thinner and thinner. We still have problems on the armpits, as always, as you know, is the most difficult part in any simulation. But overall, we have an amazingly fast and really good thing. We'll see some ways of fixing that up. In fact, I think we can go a little bit higher with this guy. I guess that will help a little bit. Yeah, it's not doing that much. Great. Okay, so now we will do a cache, and this time we will not be using a Fascia VGO. We will using an alembic. So that's how we create an alembic in Houdini. Raw alembic output. We just get this guy. Again, we will get those two nodes right here, just to delete everything. So now I don't have that much things and all those attributes from the solver, from the vellum solver. And then we will do 300 frame rates. That's okay. And you can change that obviously, but we will put like Fascia scene v1.8c, and just let's try to do the simulation. So I will stop right here, and then we will continue with the next step once it's finished. But I will tell you that doing 300 frames of a fascia, it will be like, I don't know, maybe 3 or 4 minutes. So you can see how much faster it is from Ziva. Okay, let's see in the next one. Okay, so now it comes the fun part. So we have the fascia, we simulated, it was 300 frames, 3 minutes and a half to the simulation. It's really fast. I can grab the fascia that we exported, the alembic, and do a new alembic from it, and we can see how it went. So it looks nice, but we have the usual suspects right there. You know, this kind of collision. This happens because of the muscle simulation already has some collision, so the fascia doesn't know who to follow and start doing weird stuff. You could solve it with some more substeps. Sometimes you have to put a lot of substeps, so it's really, really slow simulation. And even then, you don't get the nice result that you want. Also, you have that silly thing where you're waiting for a simulation, 8-hour simulation or whatever, and then it went completely wrong. So I really don't like this. I cannot wait. And in production, we shouldn't be waiting that much. So at the end of the day, we have a simulation that is really taking days and days and days, and you know the production should go forward. So I will explain a couple of tricks and how I do this, because right now I have this solution, this simulation that I got right here, and I think it's really, really good. It's looking amazingly good, but we just have some issues on the armpits, and that's pretty much it. So let's see how we can just fix some of that. So let's grab these two guys just to get this fascia and turn it into a polygon, so we can do stuff with that. First thing that I try always is a delta mesh. So we can grab our time shift and use that as a reference, you know, reference geometry for the delta mesh, and just this guy. And if we go to one of the problematic, just like this one, well, it makes the volume incorrect for sure, but at least we have a nicer topology. But we're doing the delta mesh everywhere. That's not really going to work that much. It really depends on what you're doing. You can just make do with that, and maybe you can just pump up the iterations on the delta mesh, even the step size a little bit, and pin the borders so the borders are at the same place that they were. You can do lots of stuff with that. Now we have something that more or less looks right, but here we have really huge just hole in the geometry going on. So another thing that we can do, we can just grab this fascia without moving at all, and we will get those guys. And this will be, I will do a fascia without simulation, really. So I can duplicate this guy and just do a point deform. And then I will deform this guy using those guys. As you know, rest point, first frame, and then you will see that this is without simulation. It is almost real time, as you can see. And it's not perfect, but we have the volumes that we want. And for sure, we can do the same thing right now. Maybe we can change, let me just grab some of these strange things. Maybe it will be a little bit better if we have more. It's not doing anything, so let's see with less points what happens. It's doing weird stuff, but I'm just looking at the volumes right now, and the volumes look more or less okay, so yeah, that's good. And again, we can do the same thing. We can just duplicate this delta mesh and do a delta mesh right there, so it will keep our fascia clean and just like the original fascia, which is this one. And you can do the fascia just like that without simulation if you want. That's not really great, but you can get some results that work pretty well. So you can see we still have some issues on the armpits there, And I don't know if they are, yeah, they are also here. We can try to do this one as they are the default numbers. And we don't have that much issues there. So now with the delta mesh, we're losing a little bit of the volume, but we have some clean fascia without simulation. This is real time. This is doing just a point deformation, and that's pretty much it. So we can just do another alignment with that to be a little bit faster. So this one is not fascia scene, it's a fascia deform, because it's just a point deform. And we will save that to the disk. You will see it's really easy. So you can do fascia like that, really. You won't have some sliding and some other complicated things that I will talk in another video, but you will have something. But the idea is that this will be like 20 seconds, 25 seconds, something like that. So in 3 minutes and a half, and then 25 seconds, 4 minutes, I have 300 frames of 2 fascias to play with. So I can just get a couple of those. I can get my fascia from here. All right, let's get that one. So you can see this is the one that we did, and this is the one that we did with simulation. Obviously, all these things that are appearing and deforming right there, they are not happening here. Same thing will happen here, I guess, where this, as you can see, this is not really a fascia. This is like, it almost looks like a skin cluster or something. And this looks much better how the muscles are moving inside the body. So this change of muscles really works. So the only thing that I want right now is to get some of the armpits of this non-simulated fascia to the other one, and we will have everything with. So one thing we can do, fairly simple, is just create an attribute, but I will paint it. Attribute paint. All right, and I will call this mask. Yeah, it's okay. So attribute paint is an amazing tool. Just hit enter and you can paint. Right now it's displaying in an infrared thingy. So when I paint, it's red is 1, blue, purple is 0. You can change that here, as you know. So you can, instead of doing it as a infrared, you can use grayscale. So this is like Maya or whatever you want. I just get used to the infrared and it's working pretty nicely. Also, you can play with volume. So this is a volume. So I'm painting also with this on the other side. You can change it to surface. So even that it's really big, it's not painting on the other side, because it just, you can see in the icon that it's just surface paint. So I will reset all changes and I will paint with surface a little bit of that around here, yeah, something like that. Maybe here, here. I have my armpits done. Great. And now I can blend those two guys just using this mask. Great. This is called mask. And now we have a point attribute, which is called mask, which is this one. Okay. And you can also, I will not do it because it's a lot of points, but maybe I can go right there. You can also try to look at that as a marker and you will see the values of each point. Great. As always, this work, but yeah. So let's merge these two. Obviously, they are blade shapeable, so you can do the blade shape, but we don't want a blade shape. We want a blade shape with a mask. There's a lot of ways to do that. I prefer to do it with a wrangle, which is your introduction in this series of VEX, which is really, we already did something in VEX with the detailed stuff. This is VEX. VEX is like Mel in Maya, is their language of programming. So what we will do is attribute P, which is the position of each point, it's equal to, let's say that it's equal to op input 1p, something like that. That means that now this guy has the p, the position of the points, just right there. So I can see in one of the ugly frames that this guy is no longer this guy, now is this guy. So we want exactly that, but we want to multiply that by a mask. So we will do alert, which is just a multiplication, where the first one will be p. So keep the points that comes from here everywhere, but use this one when mask is 1, or at least multiplied by mask. So now you can see everything is just like this one, not like this one, except the places where I painted the mask. So as you can see, we have done a little bit of work there. Let's do a little bit more here. There's still some places where that didn't work. Yeah, we have, you can see all the muscles right there. They are behaving not like this one, but like this one. But the armpits are using this. So what I'm trying to tell here is that I did that in like 5 minutes, something. I did the simulation in 4 minutes, and I already have a fascia that's really, really good. That it's 80% there, and it's doing a lot of stuff that I want. So most of the times when you're working in production, it's much better to do something like that and fix the problems than to try to get a perfect simulation, because there is no such thing. There is no such thing as a perfect simulation. That doesn't exist. So we already have our fascia. Let's try and get some skin simulation or fat simulation next. Okay, so that's it for now. Thank you. Okay, so we have our fascia already simulated. This is the one. It's looking nice. It's not perfect, but we don't need anything perfect really, because there's no such thing as a perfect simulation, and we can change the thing we want, but it's looking pretty good. And again, it's been like 4 minutes to do the simulation. So now that I have that, I can just change my inputs and I have the setup done. We will do some video on how to do the setup nicely. And then you just have to put your inputs and your output, and that's it. And you will have really fast simulations, and you will always have to do some kind of twitching and tweaking, but you will have really fast results. Okay, so let's talk about fat. For talking about fat and skin, I will do just spear right now. Really simple, little bit smaller, and maybe just like that. Just to understand that we don't always need to simulate everything for sure. So let's create a sculpt node. It's not really good. Sculpt node in Houdini. If you want to do, and you should do some shot sculpting at the end of the simulation, you should do that on Maya or another software, because that's not really that good. Okay, let's do some points. Okay, oh, come on, something like that. You can see just with 3 clicks that it's not that good, but we can do some smooth here and there. I'm just trying to create a difference between the original one and this new one. So we have that and we have that. You can see this is the distance that we have now between them. So we can do a really fast simulation just with that. I will do transform something. Maybe we just all. I will do transform. Yeah. So let's do that here. It's better. Yeah. and do transform, and I will do like a silly animation of this guy, just like frames, and then I will key that. I will get that key. I don't know how to key. Why? I don't know how to key changes. Yeah. So we will stay here a little bit, and then in a couple of frames we will just come back here. So we have this amazing simulation. Great. This is our simulation, this animation, sorry, of a sphere just going up and down. Great. And we have this guy also. So really we want this to be the driver, because this represents like the fascia in a way. I don't know if you know that there was a technique really nice in Ziva to do that, to do some just easy and fast jiggle effect there. So we can do something like that just by doing a cloth object from the sphere. This is a cloth object. Great. I will do a remesh at the beginning so we don't have that much polygons there. Something like that. Starter, maybe something like that. Yeah. Great. And now this is my cloth. Oh, great. And I will do an attach. That's the geometry. And I will attach this guy. So the attachments right now, you know, because every point has another point that is just in the same spot, there are no length on the attachment except on those ones. So the farther away from the source these points are, the more they will jiggle. Let's do a vellum solver and let's see how that works. So you can see that we have some jiggle just out of the box. I don't know if you can see that, but yeah, this is great. Obviously, it's not perfect, but it's a fast way to do it. How do you do that with fat? You can do exactly the same thing but without cloth, and instead of a cloth, just use a tetrahedral. So cloth is going to be a little slower, but now we have the inner part of that geometry. So now the simulation will try to get to maintain this distance, even though it's moving. It's trying, because tetrahedral tries always to preserve volume and to keep this attachment on the same side. So we have on the same length. So we have a nice simulation right there. We can just get this sculpt and do a little bit more what we were doing. So it's really hard to do with this sculpt thing. Well, I should just use, well, let's do it. Not fair for the guys in Houdini to do that. We can do that. But as you can see, it always, the only problem that they had is that this is not a sculpt, this is a pinch. It's updating the normal direction every time that I press the button, so that's why it's weird and how it's working. But let's just create more space right there. So now there's much more difference between this guy and this guy, and you will see that now we have a lot more simulation there. And as you can see, there's a lot of amazing and interesting things happening. Just, I don't know if you can see that, but there's some sliding right there. There's really, really nice things happening here in just 5 nodes. So this is the basic thing with the fat and also the skin really well. When you just try to fill these spaces between, just try to fill up these spaces between the fascia and the skin, and the longer it is this, the more fat you have, and really 80% of the jiggle that you have in any animal or character is the fat. The muscles are not that really that jiggly. So you can use that principle to create some easy and fast jiggle, and also to simulate the fat and the fascia, as we will do. We can for sure just give it much less stiffness. You will see now this is going to be crazy. Yeah, that's crazy. Also, this guy can use a couple of muscle steps, and you can see this really nice thing going on. Once you've got that, for sure, you can grab your object, which is the one with UVs and with everything nice. No, in fact, I will do some UV on wrap. It's called, yeah, some automatic UV. So now, if I hit that button, we can see that, and then we'll do a point deform as always. Time shift, get the first frame of the simulation, and just point deform this guy with my simulation. So now I have my render model right there doing what I wanted to do. And I don't know if you can see that there's some kind of sliding right there around here, but yeah, it's pretty good, and it's really easy to do. You can see the difference between just one step to 2 steps, right? It's changing a lot. That's too much, but you have some rotational jiggle that it's not that easy to get in a... That's too much, for sure. But yeah, well, you can play a lot with these numbers, and you can see it's really fast. I just hit this button, and let's see how much it takes to do the 100 frames. It's like 6 seconds, 7 seconds. Obviously, this is a low poly. It can be as low as you want. You can do the same thing with wherever you want and just do a remesh and get the... Even we can do something like that. And even then you will see, obviously it's going to be much faster. 100 frames in 4 seconds. And we have this kind of simulation already working. So this can be an alembic. You can do a guy that looks just like that, and do a thin cluster on it and just move it. And then you will do your guy, which look like where it is, just look like that, and just play with that. In fact, it's what we're going to do in the next video. So now that we have that, I wanted to explain that as we did the fascia just with the cloth, you can do that. You can do just with that and not do that much pressure, not do that much difference in the resonance scale, and you can just go with that. You can really go with that, and it will work pretty well for animals that has really thin skin, just like a lion or something like that. You can add a couple of attachments. As you can see, all the attached constraints have a sliding rate, and you can multiply that with an attribute. So you can paint an attribute for the sliding, and you will have some sliding. And then with something like a lion as an example, or an animal that you can really see the muscles and the sliding going on, but they don't have that much fat because they are fast and they run a lot. You can just do one pass, and with just one cloth pass, do everything. And you have you don't have fascia and fat and all of that. You just have one cloth pass, which can be almost the final skin. And that's pretty much it. But if you have, as we have this guy, which is just like that. Let's grab it. So, which is like that, and it should look like that because it comes from model, and the model shouldn't change that much. You must feel the jiggle, and you must feel all those things, but shouldn't change to something like that. That's an error that a lot of people do at the beginning because this looks so cool. So let's try to make this look like this. No, they model this because they want to see this in the render. So you shouldn't be doing this. This is just for moving this. So we can do same thing. Let's grab these guys and just put it just right here. Let's see. This is a little too much, something like that. And just a tetrahedra. Let's try to copy the same values we already have. There. Oh, this guy is going to be this guy, this guy is going to be this guy, and this guy is going to be the attachment. So we are attaching this geometry here. You can see right there the attachments. And again, same principle here. So because there's a lot of distance between those points, there will be much more jiggle here than, for example, here. And that's a little bit how the fat inside the body works. Well, it doesn't work like that, but you know, it's like the way to trying to emulate that in a way. Okay, so we already have our sim, and as you can see, it's really, really fast. We are not deforming that much, but we have the jiggle that we need. So it's really simple. It's really easy. We all know that this is the guy that the render guys want. So this is the guy that we will do. So again, point form. We can just copy and paste this one. And this is going, oh, that's not what I want. I want point deform. So let's deform this guy, which right now, moving the roll, there's no skin cluster, there's nothing there. Everything comes from the simulation. And let's just plug these guys around here. And now we have our guy smooth and all, everything is nice. There are some jiggles here and there, but I will teach you a trick to get rid of that. Because sometimes it happens with vellum, especially with these fast simulations that work with just one sub-step. But we can try and do 300 frames, no troubles. I don't know if this guy has, no, it doesn't have. Let's do another UV unwrap so we can see something happening there. Great. I don't remember how that works. I don't remember at all. Well, let's just give it that. You can see how everything is deforming. There's some stretching. Maybe we could use some skin sliding right there. But in general terms, we have really, really nice deformations. These volumes are really, really, really nice. It's really hard to get these kind of volumes and deformations just with the skin cluster. You have to paint a lot of stuff. And also we have the jiggle. So we still have some troubles in the armpits. That happens. You can fix that really, really easily just when needed using shot sculpting. And we already have really nice fat simulated, and the simulation is almost real time. Just for me, because I've spent a lot of years with Ziva and waiting for the simulation to end. So this fascia simulation that we did, and it was like 3.5 minutes. And now the fat simulation, I will just hit reset. I will just go to the last frame to see how much it takes to do 300 frames, just to keep in mind, all of you, that we can do amazingly fast iterations. So we can do lots of tests, lots of changing numbers, lots of polishing, lots of whatever you want in literally 27 27 seconds. Great. That's really, really great. Okay, so now we have that. Amazing. So next step will be to try and do some more simulations, and then we will try to make it clean and easy and do everything all at once. Great. See you in the next one. Okay, so now we have our path just right there, already seen. As before with the Fascia, you could just do a point deform with the path, and it will work also really well, and you can blend it to get better results. But I'm pretty happy with that one. It still maintained the original volumes and original model, but you can see some jiggling in the arms, and you can see really nice volumes here and there. So let's say that's great, and let's try to do the skin right now. So we will try to do some skin wrinkling and skin sliding, but for skin sliding it's really easy to do. It's not that hard, but for wrinkling, I wouldn't recommend doing that in a simulation, really, because it's not how the wrinkles work in the real world. But so we'll try to do it. So we have our skin. To do wrinkles, obviously we need a lot of geometry. That's why I don't like it, because it makes everything, let's say something like that. It makes everything really slow, but it's what it is. So vellum cloth, oops, let's do another solver. Not this one, vellum solver, please. Yeah, great. And we also need this fat themed, already themed, as a driver. So let's put it here and create an attached geometry node. Great, everything is perfect. So if I just do that and don't put as an input for the collision in the solver the fat seamed and everything, and I just disable the gravity, we'll have already some results. You can see it start to do some kind of wrinkling, but it's really hard to see. You know, in Maya we used to do that and then hit the 3 button. It doesn't exist really here, but I can just put a subdivide node here and see what's happening, and you can see that we have some wrinkling right there. Thing is that we should do some subdivision here also. I don't know if subdivision works like that. I have no idea. I think it does, right? Yeah, it does a perfect subdivision. It's not changing. I think it's not changing. Let's see what's happened here. Let's see what's happening. Yeah, that's great. So just a cloth, I didn't touch anything, and we already have some wrinkling. It's not really that good, but we can change some stuff there. So maybe we can change the, let's visualize the thickness. That this is the thickness right now, so maybe we can just a little bit thin so the wrinkles are not that thin, and also the bend stiffness, the resistance to bend, we can just put it a little lower. See what's happening. And let's see, we have some wrinkling here and there. Another thing that we can do is just get this attachment and put it really low, so it will loosely follow. The lower it is, the more wrinkling you will have. So now I think you can see we have some wrinkling, but again, it's not really a nice technique. Sometimes you get nice results there, here and there, but it's not really that nice because it's doing a little bit what he wants. That's not how it works in the real world. You know, even with Ziva and that trick that we had to do this kind of wrinkling, it doesn't work like that. So, well, the other thing that you can do, obviously, is just grab this guy, which is at the end is the one that will be rendered, and this has no enough geometry to, it doesn't have enough geometry to do some wrinkling, so we better subdivide it. And in fact, we will do the remesh from the subdivision, subdivided one. And also, we will do some UV unpack, UV unwrap, whatever. So we can hit here and see the UVs. I think we can do a UV transform, something like that. Yeah. So we can scale this guy and we can see a little bit more what's happening. And as always, point the form. And we will try to get this guy, and I don't know if it's going to be really, really different from this guy to this one. Let's see. Okay, so now we have that. Going to be a little bit slower because point the form now is working with lots of geometry, but this is a skin simulation. Unless point the form is getting a lot of points, so it does more or less like a delta mass. So if we lower this value, we'll have just the point that has closer. So now we can see we already have some nice wrinkles that once subdivided in the render time will look a little bit better, look just like that. And again, we can just play with the values, with the bend stiffness and the attach to lower the amount of attach that we are doing, and we will have much more wrinkling. But again, it's not that good. I really don't like it. I will do a video on how to do wrinkling better. Okay, so now that we have that, maybe we can just get rid. We can. Well, we could make do just like something like that, or maybe something like that. Yeah. And let's talk about sliding. It's really, really easy. You have here the sliding rate. If I just that, let's see it without the subdivision, just to be a little bit faster. You will see some sliding, crazy sliding happening right there. Just as it starts unfolding, it's really, really amazing what the sliding is doing. So that's really too much. By the way, we don't have gravity. If we put just a little bit of gravity, you will see melting a lot. Just like that. It's going down. All the geometry is going down because of the gravity. So that's too much, obviously. But we can just add on the attachment a little bit, not 1, but maybe 0.25, something like that. Between 0.2 and 0.5, you have something that works really well. And I don't know if you can see the difference, but it's really doing something. And it's hard to see right here, but I will do a couple of bakes of that one. You can see we have lots of troubles here, but that's what it is when you're trying to do all this stuff with simulations. And they are easily fixed. Don't worry about that. I won't worry that much. Yeah, you can see there's some sliding. Let's put a little bit more. Let's see what happens. But again, you shouldn't do this like that. You should use an attribute and just paint where you want the sliding and where you don't want the sliding. But because you know here is doing really, really crazy stuff. Without the sliding, you will see that the stuff is not there, I guess. So you can play a lot with that. And another thing that you can do, and we do that a lot with this technique, is, you know what, it's not that fast, but it's really, really fast. So maybe I do a simulation with the sliding at 0.5, another 0.2, another 0 without sliding. So, and maybe changing the stiffness, and I have 4 bakes, and then just painting attributes and masks. I just decide what's better for the shot and for the animation. And we usually have a setup done that automatically just does the all the simulations, and with a character like that, in maybe in 20 minutes you have everything simulated, and you have all the makes that you need to blend them, match them, and play with them, and a little bit of shot sculpting, and in a couple of hours you have your shot done with muscles and everything. So that's really the principle that I wanted to show you, that really we don't have to wait, because it's not the same to do like fire and smoke and all this kind of flip simulations of oceans and water and all the stuff. When you're doing characters, this is another animal, it's another beast, and it's really, really hard to get perfect anything. So you just try to get as much as you can, and then you just paint it, you just sculpt it, and you just try to get the sweet spot for the camera to work, for everything to work, and that's it. I'm talking about doing like some shots on a character, and 20 or 50 or 100 shots, and obviously if you have to do avatar and you have to do like 2,000 shots or 4,000 shots, you cannot do it like that. You need an army of people to do it like that, but you can do almost any character job that usually people are doing with Ziva and with this technique, and it's going to be much faster, much easier, and more artist driven. And that's the thing that I'm always looking for. I'm looking for to art direct our simulations and our characters, because if you don't do that, it's really hard to get just with one simulation. I will do a bake of this one because I think it's looking pretty nice, and I will show you the results in the next video. Okay, back to Maya, and we have the results just right here. And this one is just with a point deform, the skin as it is, with one subdivision. So we have much more geometry there, and just point deform with the fat. It looks really nice. We already have in the fat the skin sliding, as you can see, because the fat was not that attached to the fascia. So we have some kind of skin sliding right there. We have nice volumes. We still have some problems in the armpits, but as a general way, this doesn't have any skin cluster. This is full simulation, and it's looking pretty well. Pretty good. Okay, and we have also another, but this time simulated without skin sliding. So we have this kind of trouble right there, but this kind of trouble is what gives you the wrinkling. So you can just pause it here, and I just subdivide this guy. You can see right there, there are some wrinklings happening, but they are not really that good. As I said, this is not like a nice technique to do wrinkling. You can get these wrinkles and get rid of the noise, and then put them on a layer. I mean, as we did with the fat and with the fascia, we can blend them together. We can blend all those together, just painting here and there and getting rid of the noise. So we can just get the wrinkling for this one. But there's some nice things happening sometimes, and not so nice things happening in other places, but yeah, you got it. And we also have this one, which is at with skin sliding, 0.5 sliding rate in the attachment. You can see right there the sliding. It's really nice. You can see how the volume is changing, but you can see it's volume that's underneath the skin, and I guess that you can see all the squares on the checkerboard right there, and you can see how it's changing volume. But this volume that's changing right here should be up here, and it's not. It's just going sliding beneath the skin. But you have lots of problems here. We have the same thing, but 0.25, and we have some problems there, but we have really nice skin sliding also in this one. How the scapula goes out, up and down without the points moving as if it was like just a skin cluster. They are not stretching. They are stretching much more in this one than in this one. As you can see right here the checker going up and not stretching that much, and in this one is stretching much more. I just do that to see a little bit of the difference. You can see right there this lighting. And again, you can just grab this guy and paint it and just keep this part from the sliding 050, which is really nice, and not this part because we don't have that much sliding in the front. We have much more sliding in the back. And if that was, I don't know, a lion or something like that, well, they have a lot of skinning in the ribs, but they have almost no skinning in the knees. You know, you can just paint and play with that. And again, that's the idea of all these techniques, because we spent like 3 minutes and a half to do 300 frames for the fascia, and then half a minute to do the fat, really, really quick. And then all these bakes that I did here with much more geometry, they were like just over a minute. So this is like 4 minutes. So 4 plus 4, that's 8 minutes. Obviously, we didn't simulate all the muscles. This is the slower part, but maybe you can do simulation in 10, 15 minutes. So in 20, 25 minutes, maybe half an hour, you have all you need to work baked, already done, 300 frames, and then you can start just playing with it, just blending and painting masks and blend some pieces and parts from one geometry to the other, and get something really, really nice in a couple of hours. That's basically the idea. It's not to just Ziva isn't with us anymore, so we have to do another thing. But I think that with this technique, you can get almost every result that you could in Ziva, but in much, much less time. So that's pretty much it. I will do a couple of videos more on tricks and how to remove this noise and how to do some things. But that's pretty much it for now. So you can see we have everything we wanted from the beginning. I will also try and do some setup of the muscles so you can see some tricks there also. Okay, that's pretty much it. Thank you so much. Okay, so let's see a trick to get rid of the noise, the high frequency noise that we sometimes get on simulation. This also works for hair simulation and cloth simulation and whatever vellum simulation that you're doing. If you use low numbers of steps because you're in a hurry, sometimes you get this kind of results. So here I just have a sphere. I did a mountain, which is a deformer, and I put an offset the frame, so we have this kind of really, really ugly noise. We wouldn't have that in a simulation. If you see a simulation like that, it's wrong. But sometimes in some places you have this kind of behavior. So the thing that you need to do is just create a delta mesh and make it as far as you want, just to get rid of the noise. So something like that, it almost has no noise. So that's great. Even more, okay. And then what we do is what it's called a delta, which is the difference between this geometry and this geometry. That is really easy to do. I'm just doing, well, this guy, we don't need this guy for anything, really, but well, comment this guy. So I'm subtracting this information from this information. So it's a subtraction of the position of every point in every frame. So what I have is something like that. And this is just the noise, because it's the difference between this one that doesn't have noise and this one that have noise. So if I subtract one of the other, so we get just the noise. This is the noise happening. Okay, so now I just created a null to send it to chops. Chops are like the channel operators, the one for animation. And we just create a channel right here with the chop that I created here. This is just to create a chop network, and you have that. And the channel is just a channel, yes, yeah. Okay, so inside this chop network, we have a geometry, and we loaded our null that set chops, and we added a filter. This filter is what is going to be a Gaussian filter for the noise. So right now we can see we already have a lot less noise than we had here. It's much smoother, but we can make it even better just by pumping this up as much as we want. You can see now it's not a high frequency noise, it's low frequency noise, and we can just pump up a little bit that also. And now it's almost unmoving. We can just play with that. Okay, once we have the noise removed, we add it again, just like that. We add it again. We can just do that if you want, just grabbing the P from the input one and just adding it. We can do that this guy. Okay, and adding it again. So now we have almost no noise. Maybe we'll have some kind of changes, you can see, but this won't be really noticeable in a simulation. This was like a crazy noise. We shouldn't have that, but even then we can just get this really high. Something stupid like that. Maybe it's going to be a little slow to process the filter, but once we have, you can see that it's almost not. Oh, it's much better. Worse now. So maybe we shouldn't do that much of a noise removing. Anyway, this is the way to get rid of the noise, and you can do the same thing a couple of times. That's the nice thing about Houdini, that we can do something like that and get these, just like that. Here we can get our geometry, which is the chops one, which is already done. So now we can just copy and paste this guy, and I guess that the delta mesh comes here, and this is what I want up, and we have even less noise. In fact, this one, I guess, that can be much slower, just like that, maybe 5.1, and we will have a smooth transition. We still have some kind of noise, but this would be the deformation that you already have in the simulation. So this is the way to remove the noise on a jiggly and noisy simulation. That's all. Okay, now for a much more complicated thing, which is trying to do all the muscles at once, and the simulation, not just the biceps, but every muscle that we can. So let's do an object merge, and let's grab these muscles. They come from the bake from Ziva, so they are already simulated, but we want to simulate them here. So we will just do a time shift, and now we can start doing some stuff. Okay, there's a lot of ways of doing that. Obviously, I'm not a Houdini expert at all. I'm just trying to do some muscles here and there, and I found a pretty nice workflow that it works, and it's not that slow. So let's try to do something like that. Okay, first things first, we need these guys to do the remesh and to paint the attribute for the attached to the bone we have here. So let's try and do that. Okay, there's a thing that Houdini has, which is really amazing, is that you can do for each loops here in Houdini. If you know something about programming, you know what a loop is. If not, we will do just one to understand. Let's use name primitive, Okay, so I have that guy right here. The name is the attribute path. Remember the Alembic attribute path. So it seems that nothing is happening, but whatever happens here, it will happen one time each time, 52 times, in fact, for each one of the pieces that we have here. If I just click in the single pass, you can see that I can move to any one and see what's happening. So just as an example, let's put remesh right here and something like that. Yes, maybe a little bit more. And I'm just seeing the zero, the first iteration. I can see the second iteration, the third iteration, and I can start to watch all of them or all of them at once. So now I just made a loop of everyone here. You can just do that with just the arms and then the legs and then the torso and get things pretty clear, but I will do it all at once. You shouldn't do that, but it's just an example of the technique we can use. So we have a nice technique, thanks to Jordi, good friend, who thought about that, and it was an amazing thing to do. So you can do like a bounding box for each one of those. Let's just bypass the remesh for now. Let's just grab one guy, this first guy. You can do a bounding box here. Let's try and find another muscle. Oh, the biceps. Great. So we can do a bounding box just like that, right? Maybe that one, I think it's better. Okay, so we can do a bounding box on everyone without a problem, really. Let's see if we can do the oriented one, because I think it's going to look and work a little bit better. Yeah, just look at that. This is the bounding box from the biceps. Great. So let's do a sphere right there, and going to be a smaller sphere, and do a nice thing which is called copy to points. This is what people is using Houdini for environments and things like that to create some instances in points. So right now, as you can see in my bounding box, if I click here, I can see the points. I have all the points on the box. So if I copy this, you can see I have a sphere in every point. Let's scale down these spheres. Okay, that's pretty good. Let's get some more room here. And I will transfer the position, the color of these spheres to the geometry right here. So let's just grab this guy and do a color. You can do it with just an attribute, but I think it's better to use the color. And now we will do another color here. Let's put it white. Okay, so this is black, this is white, and let's do a transfer attribute. Transfer attribute, we'll try to do color. Let's do color. CD is the attribute for color. And let's try and reduce that a lot. Look what happens. I'm reducing the threshold, so these spheres can affect just a little bit my biceps. And that's how I'm going to paint the weights of every muscle. A first weight paint of the attachments of every muscle. Really, really easy and really, really amazing. Let's not use the remesh still. We will do it later. Okay, so we have this great setup for all the muscles. We just did a loop and some spheres. Great. Now we can just convert that to a proper attribute, which will be called attach point attribute. That's it's equal color X or red as you want. And so first channel of the color. So now I can just see my attach attribute in infrared. Really great. Let's just put another color here. And because we like our muscles more or less red, we will do something like that because it looks nicer and it's pretty great. There's another thing that you can do really with that, which is just create a random, not on the point, but on the primitives. Oh, let's do a random from attribute path. Oh, I don't know why this is not working, but it should work. Okay. Well, let's keep it constant for now. I really don't understand. I do another color and I put a random there, primitive. Oh, it doesn't work. Ah, okay. So let's do random from attribute and the attribute is path. Okay, that's the thing. Great. This is another way to look at the muscles, and it's really, really useful to know when they are trespassing each other and penetrating each other. So really great. You can just bypass that if you want, see it nice, or do a playlist for your supervisor or whatever. But this is really nice to work with. Great. So now we need to paint this attribute a little bit better. So there's a nice thing to do, which is exploded view. This is an amazing node where you can see everything like that, and it's going to be really, really easy to paint. Our attribute. So let's get there, and the attribute that I want to paint is attached. This is not procedural. Till here, everything is procedural, just with the balls and things like that. But sometimes you have to paint things, and there's no other way to do it because, well, I'm sure that there is another way to do it, but I don't know it. I just know my way. And believe me, this way is really, really easy to set up. So right now you can paint the attachment. Just as an example, this guy should be really attached just right here. You have to be careful with that, but you can connect it only. So when I'm painting in this guy, no, from face only. I don't remember which one it was. Oh, it's painted everywhere. Why is it painted everywhere? Oh, let's try and paint this guy out. We can go from the inside to the outside, and that's it. Okay. So this guy will be really, really attached to the spine right there. And I will start again, and I will add mirroring. So it's much easier to do. Yeah. So our model is symmetric. It's really, really easy to paint this guy right there. So we have this guy. Also, this guy should be painted like that, maybe a little bit like that. Let's do something like that. I won't paint everything and paint it really, really well, but okay. So this guy also, and something like that. Okay, we will do something like that. Yeah, great. And we will paint a little bit of that. Let's see, the biceps is great. Everything is looking really awesome. Okay, let's try. Let's try it like this. We should paint this guy a little bit more. If not, it will be falling down. Okay, we have that. Now we can just do like a copy attribute because we didn't change the vertex order. So we can paint that we can just copy this attribute, not the CD, but the attach. And we have our painted attach. Amazing. Great. Let's try and do now the remesh and everything. But first of all, we will do the group. So we can do a group expression. Let's do that. And attach group. And the expression is attach is greater than 0.5. Something like that. So this is a point group, and you can see all my points, my attachment points are great. We can then do another for loop. for each name primitive, rate, and the name is path. This is the attribute that you can read, and it's different in each one of the objects, so that's great. And a remesh like that. Okay, let's see something like that. I think it's enough, right? Yeah. So now I have all my muscles remeshed. Obviously, I'm doing it all at once. You can just group muscles, and so there are some muscles that have more resolution and some others have less, and you can do a lot of stuff here. You can always do all of these just inside groups and then merge them together and whatever you want. But this is like the fastest way to do that. Okay, so I will do a tetrahedral mesh, tetrahedral body, and I will get the conform. Let's just do one pass, see how the conform is working. And I don't want too many points inside, something like that. Going to be enough for now. And then I can create a tetrahedral subbody, and I can do it all at once. Yeah, now everything is a tetrahedral subbody. Great. Let's hide this guy. Amazing. So now that we have a group, we can just bring up our bones. Another object merge, and we'll bring up our bones just right here and do an attach to geometry. Great. And we can say that we just want a group that is called attach group. So I have only the attach group attached. Amazing. Let's do a solver just right now and collide. Let's see what happens. Okay, it's working pretty well. Just as a starting point, everything seems in place. We have a lot of jiggling. We have some stuff going weird right there, but we can make do with a little less. Yeah, sure. So we can just try and paint these guys, which are not really getting anything. In fact, these guys should be painted a little bit more, because there's no jiggle here at all. Oh, well, this part is good enough. Okay, let's try it again. And we can see right there, it's working pretty much. And also these guys should be attached. They should be attached to each other, really. They shouldn't be attached to themselves, so as to the bone, so you can create an attachment between them, but for time's sake, we will just paint it a little bit to attach all that middle part to there, and we will do the same thing with these ones, because it happens really, really fast that they just get crazy because they are not attached. So we can create a couple of attachments, not just one, as I'm doing right now, but it's just to understand how it can be done and how fast it can be. So you can see this is our muscle simulation there. It's looking great. Sometimes you feel that there's too much jiggle, but you will lose it with the fat and with everything, and you can always just try to you can always get rid of the jiggle. So the more jiggle, the better at this point. Great. So now that we have that, we can grab our original guys. Those guys, maybe we will also do this color thingy that we really like. Okay, and then we can just do a point deform to get the simulation ready, because right now we are doing it with our proxy remeshed geometry. So let's try to do that. It's going to be fairly simple. I have to thank Victor Vera, who really did this kind of setup that we're going to do right now. He's an amazing character effects artist, and he will be my boss soon enough. I'm sure of it. Okay, let's do a for each, another for each now name primitive, but before that, we will merge everything. So we have here the animated ones. If I just run a time shift, I have here same thing with that animation. So for point deform to work, I have the three things. But if I do a point deform right now, it will do the calculation of everything all at once. So sometimes this muscle will deform this muscle and so on. And that's not really good. So what we're going to do is we're going to create some groups. This one will be the base group of base. We're going to do another one, which is going to be the static group, and another one, which is going to be the scene group. Okay, so now this group is our simulation, this group is our static simulation, and this group is our static muscles from the beginning. Great. Now that we have that, we can try and merge all those. We get an error because we don't have the same attributes, because we have a lot of attributes really. So let's try and delete these attributes. Attribute delete right there. And I want to keep the P position. I don't need anything else really. Well, we can keep the UVs if we want. And for sure we will need the path. The path is the key, everything. So let's do that, let's do that. Let's see that merge. It still has some things that are not. Oh, I'm doing it the other way around. Delete unselected. Now we don't have all those, but we will need, I guess, to delete some groups. I don't know. Why is this? CD. This doesn't have CD. Okay, let's just put the CD right there. And now our merge, because he was complaining because these guys have CD, have color, and these guys won't. So you can always do something like that and just put a blank color there, and that's it. Yes. Oh. Or you can just delete the color, and there's no complaining here. Great. So now we will do for each one of the path. So this guy has path, has 52 names, one for each muscle. Also does this guy and also does this guy. We can just get that guy doing iterations. And as you can see, we have all the geometries just right there. The original geometry, the static geometry, and the moving geometry. Great. So now we can just hit delete example. And now I will delete the base group and let it not selected. That's it. Same thing with the scene group. This is the one that goes here. This is the one that it's simulated. You cannot see it, but it's simulated. Just trust me in this one. And we have the static group just right there. Great. So now we can do our point deform. And I don't know if that's complicated to understand, but we have right here this guy doesn't move. We have right here this guy that it's just there, and we have this guy that it's moving. So we can just see it working. let's just do that. And now we can just grab this guy. Get off. Okay. Okay, so we have our amazing colors and we have our model joints, model muscles, sorry, just as they should be with a nice topology and with everything simulated. So it's going to be a little bit slow because it's doing a point deform with a lot of 52 objects and a lot of points, but it works. So we can just do the simulation here, which as you can see, let's do our 300 simulation as before. Yeah, and just start simulating. Let's see how long it takes. Again, this is the fastest that you can do. You should be doing it by, not by muscle, because most of the muscles can just be the same in terms of stiffness and all that things, but you should be separating at least the hands and the arms and the legs and something like that. And you can do it in different solvers, so it's easy to control and it's faster even to just do a simulation. And if you have like a really nice shot of your arm, well, you can just change the remesh in your arm and do it. 48 seconds right now, yeah. So it's going to take a little bit longer, but it's going to look great. And we have our, I don't have enough RAM, I guess, but we have these guys working. It's not perfect at all, obviously. Well, this guy just went down, but these things happened. No worries about that. We can just paint the attachment there. Yeah. These guys should be painted a little bit more because I did a really too much with the remesh. You can see right there. If I just take a look at the attach, because it almost doesn't have any geometry at all. Maybe we can do a remesh that it's not that simple, something more like that. Just wait for it because it has to remesh 52. And now we have much more geometry. It's going to be much slower simulation for sure. But we had like a 48-second simulation in a 300 shot. So as you can imagine, this is amazing. Great. Let's just do this one and let's see how it goes. We'll have much more detail and I think everything is too much, but I think that you get the idea. Just as an example, we could do that and separate different groups like arms or legs or whatever, but you can also do tetrahedral for each one of the groups. So you can do some groups before and then after, and then a little bit like that. Okay, so that's it for now. I will do a bake of that, and I will tell you in the next one when we get to the end of that. I will tell you how long it has been. Okay, so here we have the result, and it's not really good, but it's what it is. And it was like 6 minutes and a half. So if we add the fascia and the skin seam and everything, that was around 5 or 6 minutes. This is like 12, 14, 15 minutes to do 300 frames, which is really great. And now we will try to do it a little bit better so we can just do things separately and nice. So we can just grab our guy from here. So we have our attach. All this is just to create the attach and attribute. And let's do here a null, and let's call that care like primary attach. Great. That. And now I'm going to do another merge and bring up this guy. Great. So I wanted to show the split node. It's really useful. And we will split this guy a little bit. So maybe we will grab path, always using the path attribute. Path attribute, this will be the legs. So here we will have the legs. And here we will do another split. So now we don't have the legs. We can just have like maybe left arm. Great. This will be arm. Do another one here and grab right arm. Great. So this will be right arm, and this will be the torso. Wait, toros. I'm a Spanish guy, so toros. Okay, so we have everything splitted, and this can be done in a lot of ways, but this is one way of doing it. So now we have, by the way, you hit Shift S, you convert those lines to something more beautiful. Great. So now we can start doing some, maybe we'll start with our left arm. So we can grab everything here, something like that. So we will just copy and paste that guy and everything should work. So we have our group, we have our remesh and that conform. Just put it like that, just here. And we can do just the tetrahedra right there. And it's going much faster right now because I'm just doing one arm, obviously. We can also grab this guy if we want. That's how I do it, but you can do it wherever you want. But that's really nice to have just one place to test it. So right now I can just hit this vellum solver and I can just hit play and I can see the simulation on the arm. And everything is too loose. So maybe we can add a little bit more stiffness. Maybe we can add a little bit more of the attachment. And one thing we can do is just grab this guy and do the same thing with it just here. Like that. I just wanted to show you that just copy and paste things. It's an amazing way to work. It's really, really fast. So we can write little changes and maybe we can just keep these simulated properties, but maybe we can paint a little bit inside of those. Great. And let's see how that responds. That's much better. And for sure, we can just create some more vellum tetrahedra. So we have this guy, and this guy is doing everything, is doing all at once. So maybe we can create a group. We will just use a path group. So maybe those two goes with this tetrahedra, and then we can just do another one. And this one maybe can have all of the others. So now we have two different groups that we can change damping ratio and resonance scale and the stiffness and everything all at once. So just as an example, I will try to do this simulation right now. And I'm not loving this kind of jiggle in this part here. So I just want this kind of jiggle that we already have in the biceps and the triceps, but not in the other ones. So this is the biceps and the triceps. These are the other ones. Let's push up a little bit more the stiffness. So now we will get rid a little bit of the jiggle. We still have a little bit of jiggle, but not much. And for sure, we can just come here and paint a little bit inside this guy. So it's not moving that much. It's moving a little bit, the outer part, but not in the inner part. Great. So let's try and do that. That's great. And again, just another one. Now this guy will be the right arm. Just an example. Great. We will see if we have just painted with mirroring. So if it is already working, it already has the things that we paint. So that's the magic of the attribute paint. So this is really, really good. And that guy, oh, I didn't change the arm. Why? This is not the right arm. Yeah, it is. Sorry. Yeah, okay. So we have this guy, and he's going to be really, really fast to do the simulation. Oh, something just happened here because I have these groups, and these groups, they are no longer left and right. If you do like nice naming conventions, you can just hit L and an asterisk or something like that. I'm going to do it by hand really quickly. This guy and this guy. And these will be all the guys except one. Okay. Now this should work as the other arms. Really good. But we have a lot of control right now. So if we want to do the simulation separately, we can do that, and we can just send to our farm or whatever its solver separately, so it's going to be even faster. We don't have to do that really, but I wanted to show this node called vellum pack, where we can just grab this guy, and it's packed. So now we can do the same thing with this one. And that's pretty much it. We can merge those two. Oh, not those 5, just just this one and this one. Yeah. And now you can see we have both of them packed with all the properties of the vellum simulation. So let me just grab this guy, put it over there, and you can change that so it's cleaner. And now we can just do an vellum unpack. And there's really no name here, but now we will be simulating everything is just in just one solver. So that's a really good thing because we can just do it separately. But if we need the collision with the torso, we will need to have everything packed together. So just with Y, I just put that here, and this guy will be our, I don't remember which one it was, left arm. Here, left arm vellum. Same thing with this one. This will be the right. Okay. So this solver is for testing, and this solver will be a merge of everything. It will be the final one. So let's do this a couple of times. Great. Now we have here, and we want the legs. Okay. we will see that this is not really good, but we can do recast strokes, and we have our simulation here so we can see how it was working, and I think it's also the same. Yeah, these guys are too loose, so maybe we can do something about it. This time I will do it just at once because the legs are not that important. Really, the arms is where everything happens. Oh, oh, I just did it wrong. I don't want to change this one. I want to change that one. Yeah, sorry about that. Okay, let's see the attachments and recast the strokes. And let's paint a little bit of that with the surface just to be sure that we are just getting the inner points. Symmetry is already activated, so we will paint this one and also this guy here. We could even do this a little bit better, but something like that. Same thing with these guys. That's the inner part of those. So it's not going to be that loose. Great. So let's try and delete this guy, delete this guy, and we will put it as it was. I think that was, yeah, it's not, it's 1000. Great. And let's try sim with that. Still a little bit too loose to paint. A little bit of that here, also here, and we will just paint a little bit of that here so it doesn't move that much. We don't need that movement. And in fact, we can do some kind of optimization here because the legs are not really deforming that much. They are moving, as you can see, as a group. We don't have lots of things happening here, so maybe we can just do this remesh. Something like that. So it's going to be way faster to do the simulation. Let's see. Yeah, we have some movement. We'll have something. Obviously, you can complicate that as you want and create the line of actions and everything, but just for time's sake, let's get that and duplicate it. You shouldn't duplicate that once simulated, but okay. So, and let's get the torso. Let's get this paint, cast strokes. Again, let's see the simulation we had in the torso. In the torso, it's looking pretty well. Yeah, it's pretty good. Yeah. I like it. This guy here, it's not that good. I think this right there be a little bit more weighted, so we will just paint this guy, maybe this guy also. And I think that's pretty much it. Yeah. Let's try it this way. Okay. So again, nothing changes. Everything is just separated to, oh, sorry. Doing a lot of stuff right there. So we can do this simulation right here. It's not bad at all. And because we have duplicated everything, we just have to rename this guy. And this guy will be legs. Vellum. This guy will be torso. Vellum. And this guy is the left arm. Oh, no. So So, oh, I don't know where it is, where this guy should be, but okay. Oh. Doing. I have two right arms. Okay. Not to worry. Great. So we have everything packed. So we can do some object merge to get all these guys. This guy will be this guy. Then we can just do this guy with this guy. And this will be that one. And this will be that one. So I can come here and do the simulation with everything. Everything has the attached attribute. Everything has the merge right here. Has all the vellum properties. So we have everything we need to do the simulation again. And this time we have much more control of it. Also, legs are going to be much faster. We are getting collisions with and as you can see, it's working pretty well. Yeah. Let's just copy this guy that we have here. And let's do just an alignment of that. And as we don't need almost anything, so I can do an attribute delete. So it's going to be really fast, and it's going to be, I just want the position, really, and UVs and the path. That's pretty much it. And we can keep the color. Yeah. The detailed one, so. And let's call that muscle scene one. See, oh, I'm doing it wrong. Just be careful. If you're looking at that without expression, that doesn't work. So muscle scene B1. Okay, see, you have to write also the extension, then save to disk. And this is going to be really fast. I already have 90 frames simulated, but the simulation itself will take really so little time. It's really fast. Right? We should be adding the line of actions and everything, but we have something that more or less works. So let's see you in the next one. Okay, so now that we have all these, maybe we can just clean it up a little bit. So these will be our inputs right now. As we are just getting the animation from here, this is not how you should do it. You should have the setup done with nothing at all, and then you can change the alembic or even do a point deform to make the skeleton move and then move the muscles and everything. But this should be our input. So let's call it as is. You can put here input state, and you can give it color, whatever. This is our fast setup with all at once setup. We cannot see anything here, so we can just create a sticky note. And here we can put all at once setup. And then we can grab this guy and set the text size to large, something like that. Okay, yeah, that looks very nice. And you can hide the background, those things. So Everything looks clear. Oh. Oh. Yeah. But you can understand that here, so okay. So maybe we can just draw the background, give it another color. I don't know if we can change the color. Yeah, great. So this guy right here is our input, and we can start doing all of that you can imagine. So just a split. And here we have left arm and right arm and so on and so forth. And here you can do whatever you want and everything can be really, really, really complicated. But you can understand the point of that. So everything is named and in its backdrop, you can close and open the backdrop. Nice. And maybe we should do this all at once. So this is our split muscle setup, where we define our muscles and how they are looking and how they're going to behave. And this is our joint simulation. Okay, so I wanted to show a couple of things. There's a thing that was really popular in Ziva, which is a coupled simulation. We can do the same thing here, really fast, really easy, really quickly. This is just for showing this guy, which is really this joint simulation. So let's try and do a coupled simulation, which is a thing that we did in Ziva. And one thing that Houdini has, which is amazing, I have another Houdini here open. Let me just, in case, save that. Muscle split sim. Okay, you see that I'm not even saving. Try to do that on Maya. Well, I have here my fascia, which we already did, and here we have our fascia sim, where we have our fascia construct and the vellum solver. Thing was working nicely enough. Great. So yeah, I'm going to do what you think I'm going to do. Just grab these guys, copy, and paste. Yeah, that easy. So we can grab this guy. Just we have this vellum pack, and we have this attachment. So what we could do is we have the same attachment right there, and we have some points to attach them. So you can just grab this guy right here, because the attachment, I think it's the same. No, it's not exactly the same. Okay, so we will grab maybe this guy. No, we will grab this guy, just that. Okay, and we will do another vellum pack. And then we will grab these packed objects and do an object merge. Okay, so these are all packed vellum objects. We will do another merge, so we have everything and all the vellum is just right there. And we can just unpack it. Vellum packed. Here we have vellum packed. Okay, and then we can grab this attachment there with the points that are called attach group. So they still are here, so we can just grab this guy. I don't know. This guy doesn't know what it is anymore. But this guy knows. So let's do another one of these. Okay. So you can see we still have our muscle attachments, and at the same time, we have our skin, our fascia that will do the pressure, because we already have the pressure here. So we just have to get rid of that. No, not everything, just that. Okay. And put it just right here. And the attachment is in the same place, which is with just the bones. So it will collide with the bones, muscle will collide with the bones, and the fascia will do its thing. So let's hit play. And obviously this is going to be much slower, but we are doing a couple simulations right now. So it's the same thing with Ziva. It works really well. It's slower, but the jiggling that you get and everything that you get, it's much better because you are doing it at the same time. So you can see we have some issues there, and that's the worst thing about this technique, which is that we really need to push up the sub steps so the simulation in the muscles will change. Let's say like two. Maybe we can just get more constrained iterations, and maybe, just maybe, we will get something better. I don't know if that's better. Maybe it's a little bit better, yeah. And here we can do just blast and get rid of all the muscles and everything. And I just want this guy. That doesn't have any path. But we can see the fascia simulated in a couple simulation. This is going to be really expensive, so be careful with that. I prefer to do it the other way, so the muscles work better on its own, but you can do it as you can see it right here. It's not going to be perfect, it's not going to be nice, but you can do it. Okay, so I will do a couple of sims. I will do this one, which is a couple simulation, and I will do another one, which won't be the couple simulation, and I will tell you the times, and we will see the result. See you in the next one. Okay, so the couple simulation ended. It took like 12 minutes to do everything, which is like an eternity to me. I don't like waiting for that, and I prefer to work separately, but you can do that, and here is the result. As you can see, we have nice volumes, and it helped a little bit with these interpenetrations because you are simulating everything all at once. So in fact, we can just pump up the sub steps, so it will be even slower, but it will help a little bit with these problems. Just the more sub steps you have, the better the collisions are really calculated. So okay, but we can just, let me grab from here our pact and convert, just we can play with it a little bit more. And you can also do something with that. You can see that this is ugly, but the volumes are more or less right. But you can for sure do smooth, which is a really nice node that we have. So it's much better. You can see that the volumes are still there. Maybe that's too much. You can do a little bit less, something like 5, I don't know. And we still have this kind of thing happening there. We have a strange thing happening in the in the neck. That's because the attachment for that muscle is not following the head, I'm pretty sure. But if we see in the torso, we see this attachment. As you can see, we should have this attached to the skull, but okay, we can just play with that. And for sure, we can do also a delta mesh, right? See how this works. Let's do a timesheet and get the first frame just as a reference for the delta mesh. Something like that. So these are two tricks to try and smooth it out everything. This seems to be working really nice. We still have some issues right there and in the arm, as you can see right here. So we can maybe pump up a little bit more the delta mesh, but we're losing volume. But again, as you already know, we can do lots of stuff with that. And again, it's just like 12-minute simulation to do everything all at once, which is too much for me, but I know a lot of people will do it. So I have the other scene right here. And we have, you remember from the Fascia video, we have this guy just, it's not this guy, it's this guy where we painted the attribute, the mask attribute, and blend that together. I don't know if you remember, but here you have, want to show, but yeah. So maybe we can do the same thing. Just grab these guys. Well, I don't need all of them, but put it here. And what we will do is get this. This is the delta mesh one. Okay. And this is the one that I want. So I say as always, it remembers everything, so everything works fine. And the fascia, we constructed the fascia in the other video, so it has the same topology, the same vertex number, so everything works fine. And we can do this blend. So right now, you can see this is the guy that we had, and it was like that. So maybe we can do one delta mesh with pretty high value for the missing points, and we will do another one so soft just to maintain all the volumes, but get rid of this kind of changing things, but we will still have all our volume looking great. So we will just copy this attribute, copy this one, and this one. The attribute that we want to copy, it's called mask. So now we have here, why we don't have here our mask attribute? Oh, it's called mask in lowercase. Yeah, great. So now we have this moving object, our mask, and we can blend it together with this one. So now we have this delta mesh for this part. And I think it's too much. We can paint that out. Yeah, we can paint out a little bit, but I guess that you understand the logic on that. So we have a fascia right there that it's working pretty nicely. And you can see all the volume changes and everything, and we did that. Oh, I don't know why this is looking like that. This should be looking like that, right? Oh, yeah, it's still not that. The mask attribute seems that it's not painted there, so let's paint a little bit of that, a little more. So now, yeah, that's great. All right, so we can just get rid of all of that. So this was just for showing it. And we can just put here another backdrop and said that this is like the fixed fascia, everything. And we can just render this out. This is going to be fascia blended, toolset, fascia coupled, because this one is coupled, blended, and save this is going to be really fast. And now we can go to the other file and just copy and paste. This one was the one. You can just copy and paste this guy here, which is the one that's doing the skin simulation, I guess, right? Yeah, this is our skin simulation with our point form and everything. So we can just grab this guy and copy just right here. And this is going to be our skin sim. Oh. Great. And then we can grab this fascia just right there and use it just right here. So this is our new fascia. We can see it here in real time. Looking great. There's some issue right there. But again, we will see when the form work. Working pretty nicely because the setup is already done. Lots of stuff yet to get better, but we're doing a simulation of the skin real time right now at 9 frames per second. It's not real time, but pretty fast. So we have another scene just right here where we have our volumes get there. And as you know, we can just add the skin sliding setup just right here. The one was just with the one with the point of form and nothing else. This one is the attachment that we changed and we add the sliding rate. So we can just grab that, put it just right here. And this would be the skin sliding sim. The sliding. Oh, weird. Yeah, great. So every time there's something here, it goes here. And well, in this case, it goes here. And it goes so on and so forth. But right now we have everything in just one piece of geometry where we can get everything we want. Just try and render this out. See that seam. Oh, so again, you will see how the issue simulation doing is really fast. And we have almost everything we need to call this like basic stuff. It's still not that good, but it's what it is. Yeah. Right now, you can see this guy with this fascia seam that we can just grab here. Fascia 2. This is the new one. This is the old. Oh, this is the old one. So there's a little bit of changing in the compression and also in the silhouette. I don't know which one I prefer. But again, now that I have that, this was like 15 minutes, but the other ones, the muscle simulation was like 4 minutes, and the fascia simulation was also like 3.5 minutes. So in half an hour, you can have everything you want if you want to do also the couple simulation, and then mix and match everything so you can choose whatever you want. So that's it for now. Thank you for watching and see you in the next one. Okay, in this last video, I will show how I would do the rigging and the muscle setup of everything. And let's just do a biceps. I have just right here a couple of joints with a really simple animation. And what I will do is to rig this guy here in Maya. So we have a really nice starting point. So maybe just put it right there and another one that will go just something like that, I guess. Oh. Okay, great. So now we can have this guy and this guy. And we will do a parent constraint without rotation because this guy will have the rotation from this joint. So let's do an orient constraint. Now we can do this guy and this guy with a parent constraint, and then we can do both these guys with this guy with a parent constraint, double constraint. So now we have this behavior for a muscle. Great. Let's grab this tree and just skin. Great. Now we have a skinned muscle. And then let's just grab this guy with the geometry that comes with the free asset Mr. Ring. So I guess it comes from Zebra's measure. But okay. So now we have with the Brave Rabbit Smooth tool, we have a nice and smooth biceps. And let's do some sculpting. So we will create a blend shape there, and we will sculpt a little bit this guy just to get an idea of what is happening when I just raise my forearm and the biceps is working. Let's say we have something like that. Okay, maybe that's too much, but pretty good. Okay, so now we have this change of volume, which is really nice. And you can just do like a curve then and just measure the curve and do a lot of stuff to rig in Maya, but I will do something I really don't like, but it's the fastest way right now just to show it. So let's do a set ribbon key. Great. Just grab this as ribbon, and this is rotation Z and key, and let's go just here, and this will be like that key, and we already have our set ribbon key working. And every time I just rotate this guy, the plane shape is working. Great. So let's do just one more thing in the shape of this guy. Select the shape. I will create an attribute called excitation. All right. And then I will add it. So we have here in our shape the excitation. Great. Then we will connect directly to the excitation the weight of the plane shape that we already have. So it's really easy. Just wait. And we have now our excitation working. So when it's excited is 1, when it's not excited is 0. Great. So we can just grab the geometry and create a dynamic cache, but be careful, you have to add the attributes that you want. Excitation is the attribute, so I can do that, and I have already done it, and I have it here in Houdini. So we have guys. It's not the same sculpt, obviously, but it's more or less the same. You can understand the principle here. I just found the problem with the excitation attribute that when it's 0, it breaks somewhere. So I just added like 0.001, so it's never 0. And now we have this excitation working right there. Why it's not working, but yeah, you can see right here the color of the excitation 0 and 1 when it's excited and it's when it's not. Great. So what I did here is a couple of setups. This first one was just to test what I liked. So this setup has these values, which are not the same as these values. As you can see, the stiffness and the damping ratio is changing. Same thing with the attach. The thing that I did, and that's why I want to do it like that, I'm attaching the muscle to itself. So I'm attaching the muscle to this animation. Not the bones, but this animation. So it will be always in the nice place. And also we can do something like that when you are simulating this guy. This is the kind of stiffness that I want, this kind of jiggle I wanted in the, let's do a little bit more simulation there. When it's not excited, when it's relaxed, because it's a nice jiggle, you can see, great. And I changed the parameters here just to get the one that gets excited. This one has a higher value in the stretch stiffness of the attachment. So the attachment is much stronger, and it also has the higher dampen ratio and a lower stiffness. So it follows better the shape that we have just did. So you can see that the stiffness is lower, but the jiggle is faster, which is what should happen with the muscle excited. Obviously, we can change that and we can just get to the sweet spot, but I did just quickly this one. So what we can do is we can just do a plane shape between those two. And in the plane shape, we can use the detail, this object, which is this object right here, and the excitation detail, which is the attribute of the excitation. So now we have the blend between the two. When it's stressed, it's this one, and when it's not excited, it's relaxed, it's this one. Really easy. So you can see both of them work. And we can just point deform them, and this is already the nice geometry doing what it should do. Just an example, obviously it's not perfect, but you can understand the technique right here. And even more, you can do the same thing with another blend shape, because you need to time shift this guy to not have double deformation, but we can do like another blend shape. Easy blend shape with those two, right? Because they are the same. So this guy was without simulation, and this guy will be with simulation. So maybe it's too much. I will just do like 50% of simulation, maybe 70% of simulation. But I'm getting there. No, a little less. Let's just do a little less. So that's why it's really nice to have a lot of jiggle, because you can always get to the initial point that we have rigged in Maya. Obviously, doing the Maya rig for all the muscles will be time consuming, but it's really worth it because you will have the perfect silhouettes and the perfect volumes that you want. So this other setup is more or less the same, but what I did is to grab this attribute and just remap it to match the attributes that I have here. So when this is, for example, the stiffness of the tetrahedral of this guy here, when you create this guy, it always does a group called stretch, and the attachment doesn't do by default the output group, but you can output it. So you can just grab it here, and here I have the stretch group, which is the tetrahedral, and here I have the attach group, which is the attach. The stiffness of the attach is driven by this attribute stiffness and attribute no attachment stiffness, and the stiffness and damping ratio of the tetrahedral, they are driven by these attributes just right there. So I just do some remaps to get the numbers that I wanted to get this guy. So this is that stiffness. As you can see, it starts at 1000 and it gets to 1. You can see right here that this guy is 1 and this guy is 1000. Same thing with the damping, which is 10, and when it's not excited it's 1, when it's excited it's 10. Same thing here. This guy should be 0.001, and this guy, this guy should be 0.01, and this guy is 10 times more, 10 times less in that case. And same thing here, where we have the attribute, the attachment stiffness, exactly the same. It's 1, it's 10. So you can see right here, the attachment stiffness right here is 1, and right here is 0.1. So if I look at here, you can see that this guy in the attachment is 0.1, so 0.1 and 10 because it's 1 in the other line. But I did one more thing, because if I don't do that, you can see right here when I do the simulation without the time shift, this is the node where all this is coming from. You know, we're getting to that node to get all the remaps and all the attributes as we need. So let's try and do a simulation of that, and you will see what happens. The problem with that is that it takes a little bit of time to get between one state or the other. You can see right there how it's working between two different numbers, and because it's a simulation, it needs a little bit of time to get to there. So what I did is time shift right here, and I just offset this guy a couple of frames. So you can see this guy is around here, and this guy is, I don't know why you cannot see anything, but yeah, just set it. Well, yeah, this is frame 41, and this should be frame, let's see, just right there. Yeah, you can see it right there. It's offset a couple of frames, so it will happen a little bit earlier and faster, but we still have this couple of frames of transition between them. So you can do whatever you want, but this one takes a little bit more time to get to the different states. This one takes more time of simulation because you have to do 2 simulations for each muscle. Well, for each group of muscles, you can do, as we did, some simulations on muscles, just the arms or whatever it is. But it's really, really, really fast. So it really doesn't matter. And you have like full control of everything just right here. You have like this nice jiggling in one place or the other, and even better, we can just control it with a slider, so we can say how much simulation we want. We can do the same thing with this one, obviously. Just grabbing this guy here, trying to grab this guy here, and this guy here, and again, this has no simulation at all. This has the simulation already in place. So maybe we can just split the difference to, not like that, just like that. And then we have a nice system. And this is really important because obviously you can go to micromanaging every muscle on the body, every muscle on your simulation. Once it's simulated, you can see how it's working, and maybe you can just add some keys here. I don't know, maybe it's better to do something like that with the auto key. We can grab something like that. We really love a lot more of that jiggle when it goes down, the fast jiggle when it's excited. And then maybe we can just dial it down for this jiggle, which is really too much. Go that way. So something like that. And you can play as you want that. And you can have full control of the silhouette of your muscle, the kind of jiggling that you're doing, and how much of the simulation, how much of the animation you're just using. So that's pretty much it. I hope you like it, and let's see you in another one.